Okay, welcome everybody. Today we have Fabio Bagarello. He's actually the record holder of the person with the most talks in this seminar series. And he will tell us today about a distributional approach to the inverted quantum harmonic oscillator. So please, Fabio, when you're ready, go ahead.
Thank you, Andreas. Thank you, Francisco. I didn't realize I was a record man.
That's why I pointed out.
Thank you, thank you. So this means that I'm not so boring, I presume. Otherwise, I would not have this record. Okay. So what I'm going to discuss here is something about the inverted harmonic oscillator, but from a distributional point of view. We heard something like this in the past by, for instance, by Mustafa. But it was from a more physical point of view, let's put it this way. So what I'm trying to do here is to convince you that we can do more, also some mathematics with this system. So this is the organization of the talk. And actually, before going to the inverted quantum harmonic oscillator, I will spend some time discussing Hamiltonian which is more friendly, in the sense that I can do all I want with this Hamiltonian, trying to succeeding actually in working with square integrable functions, and in particular I will be able to find eigenvalues, eigenvectors, coherent states for this Swanson-like Hamiltonian. And then I will use this as to take some limit, and the limit doesn't work in the Hilbert space, so I have to go outside the Hilbert space. This is the main result of my talk, and with this limit I will reach the proper, I think it's the proper way to discuss this inverted quantum harmonic oscillator. And again, I will be interested with the eigenvectors, with the eigenvalues, with the coherent states, and so on. And this is the reference. It's quite a recent one. So let me start with a few words on the Swanson Hamiltonian. The Swanson Hamiltonian, okay, this is the original Swanson Hamiltonian. This is the Hamiltonian as it was introduced by Swanson in 2004. And of course, if alpha and beta are different, this is not self-adjoint. And then Bebiano and other guys, they put this way. They introduced, they changed a little bit the way in which the Hamiltonian looks like, but in fact it's essentially the same. And theta is a parameter which is in here. X is the self-adjoint position operator, and P is the self-adjoint position momentum operator, and they satisfy this rule. So this system was considered by a lot of people, including myself. And one possible way to find eigenstates and eigenvalue of this Hamiltonian is to introduce, for instance, the canonical bosonic operators, which are these ones here, and then these operators here. And you see, which can be written like this, for instance, or like this if I am more interested in giving an explicit expression in terms of the position and derivative. So the point is that if theta is not zero, the adjoint of this, of the first operator, is different from the second operator, which means essentially that they are not related by the adjoint operator, but still they satisfy this commutation rule, which means that they are pseudo-bosonic in the language, in my language. And with these operators, you can rewrite the Hamiltonian, the Swanson Hamiltonian like this, with this omega theta, which you see here. And you see from here one of the reasons why it's important not to go to the limit pi over 4 or minus pi over 4, because otherwise this quantity diverges. So you can work in a standard way, which means you look for the vacua of the first operator of this A theta, and then you look for the vacuum of B theta dagger. So you find two different functions, and you use these functions like is written here, to produce more and more functions. And all these functions, this function look like this, and you see they are essentially the rotated version of the harmonic oscillator, but one is rotated in one way and the other is rotated in the other way. So here you have plus I theta, and here minus I theta. This is the point. So if you choose the normalization like this, these two families are bi-orthonormal, and they are eigenstates of the Swanson Hamiltonian and eigenstates of the adjoint of the Swanson Hamiltonian, and these are the eigenvalues, which again have this problem with this cosinus in the denominator. And we used to, with Joshua, this Swanson Hamiltonian to try to introduce a path integral for the model, for trying to extend the concept to non-self-adjoint Hamiltonian. This was, in my knowledge, one of the first mathematically oriented attempt to introduce path integral outside the standard situation. And the reason why theta needs to be here is because of this fact of the energy, the eigenvalues otherwise diverge, and because of that, because in this way you are sure that you are working with L2 functions, so square integrable function. If you go outside of this region, you go outside of the Hilbert space, and so you may have trouble. But actually, going outside this region will be very much related to what I'm going to say now for the inverted, not really now, but in a while, for the inverted harmonic oscillator. So my Hamiltonian.
Fabio, we have a question from Andre.
Yeah. I cannot.
You are mute, Andre. We can't hear you. You are mute.
Probably I just missed, but what are eigenvalues of this Hamiltonian? I haven't seen the formula for eigenvalues.
Here.
Where?
At the bottom.
These E, what are they? The energies? Or probably I just don't see it below the slide, no?
No, what do you mean? These are the eigenvalues. The eigenvalues are just this one, theta.
Probably I just don't see it on the screen for some reason.
Can you see now?
E.
Sorry. Here. Can you see now? This.
Okay. So it's almost as for harmonic oscillator, but well, multiplied by some factor, right? Does it mean that the Hamiltonian itself is kind of harmonic oscillator with modified frequency conjugated? No?
Yes. In fact, this is essentially, formally, you can relate this Swanson Hamiltonian with the Hamiltonian of a real harmonic oscillator.
By conjugation, by some conjugation, I guess.
By some operator which is invertible.
Okay. Okay, thank you.
You're welcome. Okay, now the Hamiltonian I'm considering actually is this one. So it's very close to the Swanson, which is this one, which can be rewritten in this way. So you see it's very similar, but with two main differences. One difference is that there is nothing theta depending here, which is convenient to me because in this way I have no problem with this cosinus in the denominator. And the second difference is that I am using a different parametrization. Is always I again call it theta, but this is 2 theta and here is 4 theta. So this is a minor difference. And the point is, but it's not important because now we are not discussing any longer of this Swanson Hamiltonian. We will always refer to this Swanson-like Hamiltonian, to this Hamiltonian here. So you see that formally, the reason why I'm using this is that if I put theta just formally pi over 2 or minus pi over 2, this Hamiltonian becomes this one, which is the one I'm interested in. So this is the final, the real object of investigation. But to arrive to this Hamiltonian, I want to first consider this. So the point is that since this Swanson-like Hamiltonian here is very close to the Swanson Hamiltonian, it's not a big surprise that I can find eigenvalues and eigenvectors of this one, of this operator here. And in particular, I can do essentially the same. The logic is the same. I can introduce this operator here and this operator here. And now these operators are bound, densely defined in the sense that they are well defined on the space of all the S-infinity function, which goes to 0 faster than any inverse power together with all the derivatives, so the Schwartz space, and which is dense in L2. So these operators are densely defined. These are their joint. And their joint are related with the non-adjoint operator with this formula. And what is important from a practical point of view is that they satisfy these commutation rules, which are pseudo-bosonic commutation rules for all functions in S of R. Using this operator here, you can rewrite H theta like this. And the adjoint is just the adjoint of this operator simply turn out to be the H to the minus theta. So the idea is that I have pseudo-bosonic operators. I can work with that. And there is a question. Okay. I am ready for the question.
Fabio,
yeah.
These two Hamiltonians is this Nakanishi oscillator, which I always wrote down, the non-Hermitian ones with the complex frequency and the Hermitian conjugate one. On the left side, you have omega times the phase, and on the right side, you have omega times the complex conjugate phase.
Okay.
And this commutation relation you find everywhere in this Nakanishi Hamiltonian.
Okay, okay, perfect. So this is not a surprise. I mean, it's not very different from the Swanson Hamiltonian. So imagine that somebody or that these objects are known. In fact, they are essentially proportional to the Swanson Hamiltonian. So, but if you can send me the reference, it would be nice.
Yeah, well, you have to read my papers. They are all written down there, no?
Yes, but your papers are so long sometimes.
Yeah.
It's very okay. Let me continue.
Fabio,
yeah,
it's Uwe asking. May I ask you a question concerning these adjoints of your operators? These operators are unbounded operators, and when you are using the adjoints, do you have all these domain problems under control?
Yeah, because these honestly, you're right, but the subjoint, these are the way the adjoint act on S of R. So it's not the adjoint in its full definition. I mean, adjoint with the domain.
So it's just the differential expressions.
Sorry?
It's just the differential expressions which you are using.
It's the differential expression on this set. So if you compute the adjoint of this on function which are here, you get this result.
Yeah, okay.
What is this function space? What is S of R?
S of R is the Schwartz space, is the set of all the function which goes to 0 faster than any inverse power together with the derivatives. Okay. Hi, Ali. How are you?
Fine.
The project is to construct the eigenstates of this Hamiltonian. And the way is, as I mentioned, the standard way. So I first of all look for the vacuum of a theta, and this is the vacuum. And the vacuum, I have two vacua because I have two lowering operators. This is the other lowering operator. This is the other vacuum, but the other vacuum is related to this one just by replacing theta with minus theta. And as far as theta stays is included in this interval, these two vacua are in L2 of R, so they are square integrable. Again, I take these as building blocks to construct the other eigenvectors of the Hamiltonians by making this computation here, which produce this. This is not very different from what I had before for the Swanson Hamiltonian. And this is an identity for on Hermite polynomial, which I need just a technical remark to find this result. And the other eigenvalue, the other eigenfunctions are the simplest way to derive is just to consider the previous one and replace theta with minus theta. So these are the two families. And these two families have a lot of properties. First of all, they are all in L2, at least if theta is in here. The second property are these four raising and lowering relation. Then we have this eigenvalue equation. This is the sort of the non-self-adjoint number operators. So there are these two eigenvalue equation holds. And because of exactly of these two last equation, you have this. So you get the results maybe Frieder was referring to. So the first family is a family of eigenstate of H theta, and the second family is a family of eigenstates of this other operator, the adjoint of the operator. And these are the eigenvalue, which are no longer real in this case. These families, the family that I have deduced have a lot of properties. And in particular, if I choose the normalization in this way, they are bi-orthonormal. And this can, well, actually, this is a nice exercise. That was a nice exercise to me because you can check this directly also using some complex contour integration. And I learned something I didn't know making this computation. Of course, this is also a consequence of this property here, actually. So you can avoid computations. And the fact that this is, when you take theta 0, everything collapses to the harmonic oscillator. So everything, the two families collapse and you go back to the harmonic oscillator. They are complete. The two families are complete in L2. Means that the only function, square integrable function, which is orthogonal to all the function here or to all the function here, is the 0 function. And they satisfy this closure relation, or I prefer to call a resolution of the identity. So you have this relation here, but not in L2. this relation cannot be true in L2 because you can prove that these two sets are not bases. They are just complete sets in L2. And this is, in particular, you can prove this resolution of the identity for all functions which are in the linear span, for all function f which are in the linear span of the psi, and for all g which are in the linear span of the phi. And these two sets are dense. So this is a not the best closure relation you can expect, but is a good relation. It's a nice relation. And you can also, this is nice, but you can also improve a little bit this relation. And to do that, what I did is to introduce this operator B, which maps the harmonic oscillator eigenfunction into the function of this Swanson-like Hamiltonian. This operator is densely defined, can be inverted, and the inverse gives me the eigenvalue of the adjoint, the eigenvectors of the adjoint of the Swanson-like Hamiltonian. So I can play a little bit with this, and the result is that I can extend somehow the closure relation to sets which are slightly different from the previous one. So these are technical stuff, so I don't really want to go in this detail, and also because they are not honestly very relevant. But you can do better. The point is that you cannot extend to all the Hilbert space. You can also try to look for coherent states of this Swanson-like Hamiltonian, and the idea is that what I did is to use a general theorem, which I proved a few years ago, and the theorem says that if you have two biorthonormal sets which are quasi-bases and which satisfy some relation, like some inequality of this kind for some constant, so it's not very important which kind of constant you use, it's enough that you have something like this, then you can define this series here, this series here, and this series both converge in all the complex plane. And the reason why these are interesting, these two series are interesting, is because the first, this vector here is an eigenvector of A theta of one annihilation operator, and this is an eigenvector of the other annihilation operator. So it's like the coherent states. They do what the coherent states do. And they also satisfy a resolution of the identity or a closure relation as the coherent states. That's why I used to call this pair bicoherent states. And for the Swanson-like Hamiltonian, actually, the key inequality, the key aspect is that you have to prove inequalities of this kind. And for the Swanson-like Hamiltonian, I have this and this. So I'm able to find this constant. So I can prove that these states exist. And I can also sum the series. So here is the result is given in terms of series, but I can sum up the series. And this is the first eigenstates, and this is the second, the first coherent states, and this is the second coherent states. And they are reasonable in the sense that if you put this and you send this to theta to 0 in these two formula, you go back to the coherent state, to the standard coherent state of the harmonic oscillator. So they look like reasonable results. Now let's go to the more interesting.
Fabio, one question.
Yeah.
These bicoherent states, do they minimize the uncertainty relation?
No, in the sense that, for instance, this one minimize the relation if you define, if you change the scalar product. So putting some measure or some metric operator. But when this minimize that particular definition, then this does not. So that's why the two are interesting together, because you cannot choose one, because if you just choose one, you destroy the properties of the other. So they go together, in my opinion.
But it's also tricky to talk about minimum uncertainty, because X and P are not strictly observables here. So what uncertainty are you talking of?
Well, the corresponding one, the observable, the corresponding X and the corresponding P, of course.
But
okay.
Joshua, you can always define something like this. No, you take you have in any case operator which have some commutator different from zero. So you can
yes, but they have to be Hermitian because you are using the hermiticity in the proof.
Yeah, you're right. You're right.
May I comment here, because I constructed a similar coherent states with this creation and annihilation operators, but I didn't use the variable X, but a variable Z, which picked up somehow this complex phase. So in a sense, I got a coherent states which minimize the uncertainty relation and allowed to move the oscillator in the complex plane on ellipses like Carl Bender did in the classical limit. So when you pick up this complex phase such that it gets negative, somehow you invert the oscillator, or it gets imaginary, you invert the oscillator and you go to a certain limit where these classical trajectories are in a circle cone in the complex plane. But in general, the coherent states, they minimize the uncertainty relation. The only thing is that the expectation values in configuration space that are not necessarily real, they can be complex values.
From this point of view, I don't fully agree. It depends. There are a lot of people working with coherent states in very different area, and there is not, in my knowledge, there are very well, very big intersection of what people believe are coherent states. So we must understand each other of what a coherent state is really for me or for you or for.
Well, maybe I should talk in December about this model in complex space, and then you will see that they are coherent states in the standard sense. The only thing is that expectations value can be complex and not real valued as you see it. And between these two Hermitian conjugate Hamiltonians, you have a metric which relates them.
Okay. Okay. May I continue?
Please, Fabio.
So let's go to the main object of my talk, which is this Hamiltonian here. And the idea is that formally, this is exactly the Hamiltonian I had before, and I can recover this just by fixing theta equal to pi over 2 or to minus pi over 2. So the reason why I'm saying formally is because what I'm trying to do is to give a mathematical background to these results, because formally I can also take the eigen functions of the Swanson-like Hamiltonian, just taking theta equal to pi over 2 or minus pi over 2, and this is what I get. And these are functions, of course. No doubt about this. Is the Hermite polynomial with some term here. The point is that, as you see here, as it's clear actually, these two functions, these ones and the dual family, the eigenstates of the Hermitian conjugate of this, which is formally the same. That's why this is maybe a comment which I have to do. In the Swanson-like Hamiltonian, I had two Hamiltonians which were truly different. So H theta and H theta dagger were really different. So I had two different families of eigenvectors, this phi n and psi n. Here, if I take theta equal plus over 2 and or if I take theta equal minus pi over 2, I get the same. So this is reflected by the fact that the second family is exactly the first family with plus and minus exchanges. But the point is here. The point is here. It is, I guess, it's well known to many of you that these are not square integrable functions. So this is the L2 norm, and this norm are just diverging. Still, I can try to introduce the operators, the same A and B I introduced before, just by taking theta, fixing theta to these particular values here. And this is not really, Ali? Ali, I'm waiting. No, you are muted.
Okay. The thing that bothers me is that you are introducing operators without introducing their domains.
No, I'm doing. Next slide. So give me some seconds.
Okay.
So this is formal. All you see here is formal. But the operator of this kind are again densely defined. So I'm not really caring about a domain. I'm caring about what people, mathematicians call a core. A core is a dense subspace of the Hilbert space where all these operators can act. And all these operators here that you see here are very well defined on this set of test function on this Schwartz space. And you will see that also this Hamiltonian is well defined. But this is not very relevant to me. This is not the point I'm interested in. In any case, these operators here, the ones you see in this line, they are densely defined on S of R. So it was written already actually in this slide, and can be repeated.
Isn't that true that then the adjoint of these operators should be defined on distributions?
This is more or less the similar question to Uwe's one. So what I'm doing, what I'm saying here is that you can extend maybe you can extend actually no, maybe you can surely extend the definition of this operator on something larger. And this is in fact what I do here, but you must be patient once more. But the point is that from a mathematical point of view, to be safe, to feel more comfortable, what I want to check is that I can act on this with this operator at least on some dense domain in the space. So what I care is to have a domain which is dense in the space in L2 and which is stable under the action of this operator. So I am sure that if all I'm doing here is well defined. For instance, since fx, this function here is in S of R, the action of this commutator is well defined. I can act with this on that. I get another function which is a test function in S of R. So I can act with this operator on this new function. So I'm sure what I'm doing is well defined. Then you are right, these operators, at least to me, the interesting part is that I can extend outside the space. So I don't know if you have this in mind, but for instance, if you see this formula, which are the standard ladder equation. So the lowering equation, the raising equation, and so on. You see here, I'm acting with A plus, for instance, on distributions, on something which I will discover are distribution. For the moment, I am not reached yet this point, but the point is exactly what you mentioned. This is a distribution. This is a temperate distribution. This is what I'm going to prove in a moment. It depends on you, of course. Okay, so I'm
Marco has a question, then Andre, and then Uwe.
Wow, too many questions.
Yeah, I'm just wondering. Okay, so you have this operator which is densely defined, and even powers of it, I guess, the same, of course. But what if you would look at the evolution that this operator generates?
No,
would you know a domain that's dense that is left invariant by the group of evolution?
No. This is quite an interesting question, but I don't know. I don't even know. I can think about that, but it's not so. I have not a fast reply. I cannot reply soon, so I have to think about that.
Okay.
You're mute, Andre.
I have a simple question. So you have a letter N in your slide. Does it mean that you claim that the spectrum of the inverse oscillator is discrete?
I'm looking for the discrete part.
Okay.
I'm not claiming I know anything about the continuous part. This I don't know.
Well, I thought that the spectrum of inverse oscillator is continuous with the energies going down all the way to minus infinity. It's the same as for linear potential. If you have just the potential constant times x, just electric field, then the eigenfunctions are area functions, and it's continuous spectrum, and it goes all the way to minus infinity. And I thought that it's the same for inverse oscillator. And moreover, I discussed once this question with Didier Robert. He is a mathematician at the University of Nantes. And he just confirmed it and even gave me a reference for his book. He has written a book on coherent states. And this statement is there, which is for me very natural. So, but you say something different, right?
Yes, I know the book by Robert. I know him. I met him a few times. Actually, I'm not completely sure we are using the same language, because since what the eigenvectors that I will find are not in L2, no? So
yes, because continuous spectrum, of course, it's not an L2.
But I'm always referring to the discrete part. In any case, I'm referring to the discrete part. So I'm not saying anything about the continuous part of the spectrum.
But what distinguishes the functions which you wrote from all other functions, which also can be written?
Sorry.
Just I'm asking what distinguishes your functions, which you written, from some other functions. You got, as far as I understood.
This is the function. Actually, I will be. You are asking question before I'm going to be how to say rigorous. So this is formal. So I really. What can I say is that this object, this function here, is a solution of this equation. Is a formal solution of this equation.
So the energy is imaginary.
Yeah. Yeah.
That's some completely different functions, because I thought about the states with real energies.
No. This is completely.
Okay, so it's different function. Okay.
Okay. Uwe?
Yeah, very simple observation. Why are you just forcefully trying to remain in the L2 over the real axis? I'm wondering. Just define a Hilbert space, another Hilbert space over a path in a complex plane, just using a holomorphic extension from the real line to some line under this, how to say, on this Stokes wedge actually, and there define the Hilbert space. And it seems your problems will be gone immediately. You are just getting a kind of rescaling, and that's all. But I may be wrong, of course. Did you try something like this?
No, I honestly, what can I? The truth is that I don't like this way to approach the problem. I mean, I have a problem. It leaves at least the problem, as I consider, lives in the real line. So I understand I can go to complex, but I prefer to avoid. I want to see, if you wish, is a different way to look at the problem. I want to stay on the real line, and then I want to. This creates, for a mathematician, I would say, an interesting, many interesting consequences, because you get eigenstates which are no longer in L2.
No, it's just a different L2. It's L2, but over this path in the complex plane. It's a differently. All your problem is reducing actually to inequivalent Hilbert spaces.
You see, this is what I wrote on the side. I use the complex variable Z and the complex variable Z Tagara, and you can formulate in this variable Z square integrable functions, and you can construct in this variable Z square integrable functions. But Z and Z should be considered independent. Yeah.
Sure.
This is, I guess, is very much a matter of test. So
sure.
No, because my oscillator moves through the whole complex plane. Yours is fixed to a certain values of Z or real.
No, absolutely not, Frieder. No. This is not true. I can change.
Look, I can prove this. It's very.
Frieder, we are discussing Fabio's model here.
Yeah. Okay, Fabio. So maybe we can discuss this point afterwards a little bit in order not to disturb your.
Okay, talk. With pleasure.
Okay, thank you.
I guess there is.
Ali has a question as well.
I had just a comment. This operator inverted oscillator, you can actually show that its spectrum is whole complex plane, not even real continuous. It's the whole complex plane as far as I know.
This I don't exclude. It goes back to Andrei's question. So what I'm focusing on is on the discrete part of this Hamiltonian constructed in this special way. So these are eigenvalues for sure. Eigenvalues, not even eigenvalues in the standard sense, but because in the standard sense, I repeat, you are working in L2. We have function an Hilbert space, and the eigenvectors is a function in the Hilbert space which has some property. So that's the definition of eigenvectors. Here, this function which I have here are not in L2. Going back to what Uwe says, maybe there is another way to deal with the problem. But if I want to not to go to the complex plane, then a possibility for the for this generalized function. This is what I can prove. That is that these objects are generalized. Let me call generalized eigensets of H plus or minus. And let me repeat. Let me stress once more that so far, this is just formal because I'm still need to be to go to the rigorous part of the talk in dealing with this object. So these are functions, are this function here, but I would like to put on to prove that these are distributions, which is what you mentioned or close to what you were mentioning before. So what I'm doing here is just to look at this operator from a very formal point of view. So caring very little about the mathematical details, just as taking what I learned from the Swanson-like Hamiltonian, fixing theta in this way or this way, and see what happens. Now I guess it's time to go, because otherwise I still am formal and you don't understand what is the point of my talk. Now what I'm doing is to prove, and this is a different story, to prove that this object here, that is this function here, this one, and in particular the plus for the minus is the same, is a temperate distribution. So this defines a temperate distribution. This is one of the results of this talk. So what this means is that I'm using the eigenvectors of the inverted harmonic oscillator with these eigenvalues that I showed before. They define temperate distribution. This is one result. The second result that I will prove later is that these are weak limit of functions. So they are weak limit in the sense of distributions. And then there is a third result, which will come later, if I have time, and which will have to do with the coherent state, which is even more complicated situation. So let me prove this, that this object is a temperate distribution. And to prove that, the first thing that I have to do is to prove that this is well defined, because otherwise I'm talking of nothing. And to prove that this is well defined, I just compute the explicit expression, which is this one. And f is a test function. So I have to compute to prove that this is well defined means just to prove that this is finite. So I have to compute this integral, to estimate this integral. But this is the Hermite polynomial, so it's a polynomial of degrees n. And this means that I can divide and multiply for another polynomial of degree n plus 1, and this integral is surely finite. So this quantity is less or equal to this quantity here times this sup here. And this sup here, so these are technicalities, so I'm sorry, but this is just to show you that there is some mathematics behind my claim. This sup here can be written like this: it's a finite sum of semi-norms of the topology which define the topology in the Schwartz space. So summarizing, I have this. I am able to prove that okay. This object is well defined. This is what this means. Then it's linear, and what I still need to prove is that to check that is a temperate distribution is that is continuous, which means this. I take a sequence of function in the Schwartz space convergent, then these objects should converge. And again, this is a small theorem, but it's not completely trivial, because I have to prove that this quantity goes to 0. This quantity can be estimated is just rewritten like this, which I can rewrite like this, dividing and multiplying for the same quantity. And this is an L2 function. Let me stress that this is not an L2 function, but this ratio is an L2 function. These are functions in S of R, which means that this is an L2 function. So I can use the Schwarz inequality and I get this results here. So the idea is that I can prove that this is also the functional I introduce is continuous. So this is the proof of this, of my first statement. This object is temperate distributions. And the second statement is that the second that I already mentioned. So they can be defined or recovered as weak limit of the function of the Swanson-like Hamiltonian. So that's the reason why I introduced the Swanson-like Hamiltonian. So you start with functions which are in L2, you take this limit, you know you are going outside L2, but you get temperate distribution. So the results that you get, these eigen functions, these generalized eigenfunctions of the inverted quantum harmonic oscillator are temperate distributions. And this can be done with the plus, with the minus, with the other family. So this is not a big problem. As for the bicoherent states, Ali, please. No, you're muted. Sorry, Andreas, I'm taking your, I see.
You're muted, Ali.
So when you say temperate distribution, the examples that you give, they are functions. So you only try to show that they decay fast at infinity, right?
No, they don't decay. They don't decay.
I know. I mean, they don't decay, but they are functions. They are functions which don't belong to
L2. They are these. So they are these objects. So they are functions.
They are functions.
Yeah.
Because distribution means something more general than the function. So it need not be function.
No. The distribution are also something more general than function, but functions not particularly good are also distributions.
That's right.
Okay.
Yeah.
Okay, let's go to coherent states. Coherent states, I cannot use that theorem I mentioned before because that theorem, as I mentioned, was based on estimates of this kind, while I have this kind of relation. So no way. Nevertheless, if I just act formally on if I just the bicoherent states I introduced, I found for the Swanson-like Hamiltonian, and I just formally put theta equal to plus or minus pi over 2, I get these two functions. Again, Ali is right, these are functions, but which kind of function? And these are very bad functions because they have this behavior, they have an exponential growth essentially. So this means that they are not even temperate distribution. I cannot claim that this object here are temperate distribution because they are not. So if I want to use the same distributional approach for the coherent states for this inverted harmonic oscillator, I need to do something more general. And this is the idea. So I first construct a set of, let me call, nice function. Actually, they are not, S of R is made of very nice functions. These are useful function. Let me call them useful functions. So I start with a fixed function here, and I define the function of square integrable function, which when multiplied by this fixed function, they stay in L2. And this set is very large in the sense, of course, it depends on how rho of x is taken. But if this is an L-infinity function, this is exactly equal to L2. And if rho of x is continuous, then this you can prove that this set is dense in L2 because it contains the set of all the C-infinity function with compact support. So we can put a topology in here, which is what you do, for instance, for the test function. For the test function are nice because you can put a topology and the set of the test function is closed with respect to this topology. Here I introduce a topology which I call tau rho, and I said that a sequence is convergent in this topology if this is norm Cauchy and this is norm Cauchy. So this is the definition of the topology. And a lemma says that if rho is the inverse of rho is bounded, then this set is closed. So this is a nice set to work with. And I can introduce, there is a question.
Yeah, I'm just wondering, is this the same as saying you just changed the measure from Lebesgue measure to square root of rho times the Lebesgue measure or something like that?
Well, I didn't consider this point of view, but maybe you are right. Maybe there is not so different. Yes, maybe you're right.
Okay, thanks.
You're welcome. And I can introduce a sort of dual of the rho, which is this set here, where you see here, the point is that I have the inverse of rho, and I'm asking to this object to be square integrable. And again, I'm dealing with functions. Going back to Alice's question, comment. Now we can prove that this set is inside the dual of V rho, in the sense that is okay. It's very hard to go.
So,
but
what do you mean? What do you mean by inverse of rho?
Rho is a fixed function which is positive, so it has an inverse. It's a function. It's a function. Rho.
Inverse of a function means that it's 1-to-1.
No. Rho means, sorry. Now I understand your question. It's just 1 over rho.
Okay.
Okay. I was here. So I can prove that this set is inside the dual of V rho. And the proof is very easy because, first of all, this means that taking an element of this set, I can define a linear functional on V rho, which is continuous in the topology of V rho. So let me skip the details which are here. You can do that. So you can define any function which is in here, define a sort of distribution on V rho. Okay. So going back to the inverted quantum harmonic oscillator, for the inverted harmonic oscillator, rho of x is this one, which is continuous. So so this is my choice, of course. So this means that this set is dense in L2 and is tau closed because the inverse is in L infinity. So it has all the properties which were required here. And now I can check that these are not temporary. These are the bicoherent states which were ugly objects are here. So they were growing exponentially. But still, they belong to these sets, and therefore they are this sort of distribution on the row. And Andrei, can I go to the end? I'm finishing. We might. And they satisfy this resolution of the identity or this closure relation here. And they are weak eigenstates of the annihilation operators. For instance, I have this relation here. So since they are not, to me, are a sort of distribution, what I care is the sesquilinear form you see here. So they are eigenstate of the annihilation operator, but in a weak form. They satisfy the resolution of the identity. They are not temperate distributions. Still, they are dual. They are continuous functional on some different space. And okay, let me just conclude. Okay, this is a summary of what I did, but I guess there is no reason to repeat everything, and let me advertise my book. And that's all. Okay, that's all.
Thank you, Fabio.
Thank you.
Thank you, Fabio.
And more questions, Andre.
Okay, so can you show again your expressions for eigenfunctions, which you can see?
Eigenfunction.
Eigenfunctions of inverse of the inverse oscillator.
This one.
Okay, do I understand correctly, or probably not? They don't grow up at infinity, or they do?
They do, because of this. Yes, of this Hermite polynomial. They have a phase here. This is a phase.
Yes.
But this is the Hermite polynomial. So they grow potential as a power of degree n.
Grow as a power, right? Not exponentially.
Not
So,
exponentially.
okay. So I'm not quite sure, but my impression was that these eigenfunctions with real energies, which I mentioned, they don't grow at infinity, but or they are not square integrable. So it's like exponential of IPX, but much more complicated. They don't grow, but they look like this wave with the momentum which depends on the position, right?
Sorry?
My impression was that the eigenfunctions, which, well, I discussed with Robert, with real energies, negative real energies, they don't grow up at infinity. But or they are limited, they are bounded, but they are not square integrable, of course, as yours. So my impression, well, maybe that's not the case. My impression that you picked up some particular functions which are eigenfunctions of the Hamiltonian, but the eigenfunctions that you discussed make measure zero compared to all possible eigenfunctions, if I understood correctly. Do you agree with that?
No, I cannot agree in the sense that I don't know the results you are referring to, but I can read. They are in the book by Didier.
Yes, but I gave the reference in the discussion.
No, I'm not.
And for me, it's natural because it's like the linear rising potential. Inverse oscillator is similar physics, is similar to the problem with linear rising potential. That's the only thing which I want to say. Okay, thank you.
Thank you.
Frida.
I mean, if you have a harmonic oscillator, you work with trigonometric functions. Now, if you take the inverse inverted oscillator, you choose a complex or imaginary frequency, so you work with hyperbolic functions. And they are the movement of these hyperbolic functions in a sense where they are square integrable. They are on complex contours which are not the real axis, but they are inclined to the real axis. So this is why you can build the whole L2 wave functions in the complex Z plane, but not on the real axis. And so if you go in this limit where you take imaginary frequencies, you have two complex lines in the complex planes which are crossing, where which are somehow the directions where the classical particle will move to when it goes to infinity. Yeah. So when you work in the wrong direction, then of course you don't see all this. But if you work in the right direction, you will see tempered distributions and all that.
Yes. As I mentioned at the some moment, honestly, I don't know what you mean by the right direction and the wrong direction. This is not clear to me. But you know,
yeah, you were working with this variable x and not with the complex variable z in a sense, and so this is why you have the impression that your Hamiltonian and the Hermitian complex, the Hermitian conjugate Hamiltonian are somehow the same up to taking the complex conjugate of the frequency. But if you have a complex variable z, then you have 2 degrees of freedom and not only 1 real degree of freedom. And
yes,
this makes a big difference.
But you see, at least to me, this is your point of view, which is a possible point of view. My point of view is slightly different. I mean, I have a system. I have a very general strategy, which are ladder operators, which works perfectly fine for many models we well known. So I was following this idea and trying to understand how far can I go. And okay, this is how far. What I discussed today is what I got with this particular model, following this idea. But I'm not claiming this is the most general approach to any model. I mean, this is a possible way to look at the model. And for sure, what I know is that, what I hope at least, is what I'm saying is correct. So it's correct from a mathematical point of view. Then we can discuss if it's physically interesting or not. This is, of course, another story. But what else? For sure, there are other possibilities. I'm very much interested in looking. I know very much that I of course know that there are other models, other possibilities. Andreas, for instance, he doesn't use bicoherent states. I know his work use coherent states even in presence of non-self-adjoint Hamiltonians. I'm not claiming that is wrong and I am right. There are two different approaches to discuss some physical problems. So I don't see. I imagine that any idea in this new area are welcome. So it's just opening our mind. Maybe I will listen to some interesting. For sure, today I got some interesting ideas. So I will study this your paper and book by Didier and see if some more idea comes to my mind. I hope you do the same with my paper and that you buy my book. Okay.
Miroslav,
Fabio, please, could you make me a favor and display the last transparency with conclusions? It was too shortly exposed.
But the conclusion was essentially nothing but what I did.
Of course, but it would be better to have it.
So I never
Thanks.
had so many questions as today.
Yeah, thanks.
Fabio will also send us the slides, and they are made available on the website if you want to look again, Miloslav.
Okay.
Any more questions, comments? Let's thank Fabio again for this nice talk and for answering very patiently all the questions.
It was a pleasure, actually. Thank you very much, all of you.
Thanks very much.
Thank you. Good day, Fabio.
Bye.
Many thanks.